In this screencast, we're going to explore the acceleration of point P with respect to point O as observed in an inertial reference frame, but expressed in a polar frame, which we've defined as an E sub r direction and an E theta direction. And we're going to put this in the context of a familiar case, which is the circular path of point P around point. And the ultimate goal here is to understand these expressions of acceleration, which are probably a little bit unfamiliar. The r double dot minus r theta dot squared in this ER direction, and then the 2 r dot theta dot plus r theta double dot in the E theta direction. Velocity is a vector, which means that it has both a magnitude and a direction. And if particle P is moving counterclockwise, then we can draw our velocity vectors as it's moving around the path to look something like this. And to form a geometric representation of acceleration using our velocity vectors, we can zoom in on this time in which we're showing point P. And so if we have a velocity vector at this time t, and then a short instant after that we have another velocity vector at time t plus delta t. This would be in the inertial reference frame, and this is of point P. Then we're showing here a change in the velocity vector. And we'll see in just a moment that the change in velocity vector from time t to time t plus delta t is due to two different things that are making this velocity vector change. And still looking at this from a geometric perspective, the acceleration vector is going to be the vector from the tip of the velocity vector at point t to the velocity vector at t plus delta t. So this is the acceleration vector as observed in the inertial reference frame of point P at time t. So let's move this off to the side, still understanding where our acceleration vector came from, and then we'll draw our acceleration vector onto the particle now so we can interpret this in light of the polar frame, which is in the ER and the E theta direction. And so first, sketch a polar frame onto your system diagram. And so here we have the polar frame B, which is defined by the basis vectors ER, E theta, and EZ, where ER is always pointing from an inertially fixed point to the point P. We have EZ, which is out of the page, and then E theta, which is the cross product of EZ with ER. So let's glance here about the circular path around point O. And what that means is that our radius doesn't change. And if our radius doesn't change, then that means that r dot is equal to 0 and r double dot is also equal to 0. All right, now we're set up to start making some sense of all these terms up here. And let's start with the E theta direction. So the E theta direction we know here is pointed up and to the left as we're looking at it here, which is tangential to the path. And so we've just said that r dot is equal to 0. So up here in this term we can just ignore this term, and that means that we're only left with an r theta double dot in the E theta direction. And so this is in the E theta direction, so let's draw that component which is tangential to our path, r theta double dot in the E theta direction, and we can see here that it's the E theta component of our acceleration vector which we've already drawn for our particle P. Now on a circular path, this E theta direction is the only direction that we have velocity, because remember, velocity is always going to be along the path of the particle. So if r is constant, then the only thing that could be changing here is going to be theta dot. So that means we have a theta double dot term, which is either positive or negative, and here it's pointed in the positive E theta direction, which is telling us that this particle is speeding up as it's going around this path. So let's understand that by looking at our geometric diagram here, where we have our velocity vectors at time t and t plus delta t. The length of the velocity vector at time t is shorter than the length of the velocity vector at time t plus delta t. and that's telling us that it's speeding up. Mathematically, we would express this as the norm of the velocity of p at t plus delta t is greater than the norm of the velocity of p at time t. And the norm here, essentially just saying that this is the magnitude of the vector. So let's quickly examine a hypothetical case that says that instead of p speeding up, that it's actually slowing down. So that means that our velocity vector at time t compared to the velocity vector at time t delta t would be just the opposite. So if the velocity vector at time t plus delta t were much shorter, as we're drawing it here, then that means that our acceleration vector would be pointing from tip to tip, which is in a completely different direction than we're drawing here, but look at where the e theta component would be. Our r theta double dot in the e theta direction would be pointing in the opposite way, meaning that, remember, r stays the same, but it's theta double dot, which would now be negative, which would point us in the negative e theta direction. Now let's switch gears and take a look at this radial direction, or the ER direction. So here we have an r double dot minus an r theta dot squared in the ER direction. And we said that r double dot is equal to 0. So similarly, we can ignore this first term on a circular path, and that leaves us only with a negative r theta dot squared term. So let's go to our system diagram, and it's r theta dot squared in the negative ER direction. So drawing this here, we have an r theta dot squared in the negative ER direction. And we see that this is the perpendicular component which creates or finishes this acceleration vector as we've drawn it before. So notice that this term is always going to be pointed toward the middle of the circle. So it's always in the negative ER direction no matter what happens, because r is positive, and then theta dot, whether it's positive or negative, is going to be a squared term. And this term we call the centripetal acceleration. And let's contrast that with this, which we often call the tangential acceleration. And the differences between the two is that we've already said this tangential acceleration is telling us about the particle speeding up or slowing down along the path that it's taking, along the circular path. And the other element that adds to an acceleration, the centripetal acceleration, is not telling us about the speed of the particle, but it's telling us about the direction that the particle is traveling. And once again, we're going to get insight from that by coming back to our geometric representation of our velocities, because regardless of what happens, of the length of these velocity vectors, the direction that these velocity vectors are pointing is naturally going to change as the particle goes around the curve. And so we see these two different contributions: the change in speed, the length of the velocity vectors, and then the orientation or direction of the velocity vectors, which keeps the particle on the path that it's traveling on. So let's make a quick application of Newton's second law to the problem of this particle speeding around this circular path. We know that Newton's second law says that the sum of all the forces on particle P is equal to the mass of the particle times the acceleration of the particle as observed in the inertial reference frame. And as a quick reminder, I should say that when we're dealing with either velocities or accelerations, it's not necessarily to put the point with which it's referenced, because it's assumed that it's referenced to any point that's fixed within an inertial reference frame. So that's why you'll see me occasionally, just putting P, or occasionally putting P with respect to O, and you'll see that on the velocity terms and the acceleration terms. That, however, is not acceptable when creating a position vector. It must always be referenced to a point. And so we always take our left-hand side from a free body diagram. And so on this free body diagram of particle P, we have a scalar F sub r in the ER direction and a scalar force F sub theta in the E theta direction. So plug this into Newton's second law. Then we'll equate our coefficients for E sub r, and then equate our coefficients for the E sub theta terms. And you'll notice here that these two equations serve two different purposes. Let's take a look at the E theta equation because it's along the path that we have. E theta is always in that direction. And we'll see that we have an equation of motion which says that theta double dot is equal to the F sub theta term divided by mr. And because F sub theta is always going to be pointed along the trajectory, then if F sub theta is in the positive direction, it's going to be speeding up as we go around the circular path. And if F sub theta is negative, it's going to be slowing down or decelerating and eventually would turn the particle around to go clockwise around the path. By way of a practical example, if P is a car that's traveling around this circular path, if it's accelerating, then this is the force, F theta in a positive direction is the force that's being applied to the ground from the tires. If F theta is decelerating or negative, then that would be the braking force that would be decelerating the particle as it goes around the circle. Now let's take a look at this F sub r term, which we say is equal to negative mr theta dot squared. Now, instead of this being an equation of motion, we see that this isn't a second order differential equation, but we call this a constraint equation. And so F sub r is pointed in the positive E sub r direction, and to cause this centripetal acceleration, F sub r needs to be negative. So it needs to be negative ER direction, so the force needs to be pointed in that direction for the particle to stay along the path, because remember, this centripetal acceleration is all about the direction of the particle for it to stay on the path. And so staying with the example of a car that's going around this constant radius, then this constraint force, F sub r, is going to be the friction of the tires in the lateral direction as you're going around the path, because as the tires turn, in this case to the left if you're the driver, then the friction is going to prevent the car from skidding and keep the car on the path in the direction that the driver wants to go. Now, to aid in our understanding of what this centripetal acceleration is doing, I want to change reference frames for a moment. So far, we've done everything from an inertial reference frame. So it's as if we're sitting back and we're watching the car, in this case, go around this circle. And we're talking about the forces that are being applied to it. There's a force that's accelerating it around the curve, and then we've got a constraint force which is keeping it on the curve. And remember, what's so special about making observations from an inertial reference frame is that Newton's second law applies. That's the only place we can apply Newton's second law. But now let's approach this as if we're actually sitting inside the car and we're going around the circle. Now, we're going to be in a non-inertial reference frame. And we know that because even if we're going at a single speed around the curve, which means that we wouldn't have a tangential acceleration, because we're going around a curve, we still have a centripetal acceleration, which means that we're non-inertial, we're accelerating. And so imagine yourself sitting in the passenger side of this car. And so you're going around this curved path, and then what you're feeling is you're feeling a force that's trying to pull you out of the car. And this force has a name. It's called a centrifugal force. And in reality, this isn't a force at all. So it's a fictitious force. The reason why it's a fictitious force is because if you put yourself in the inertial reference frame again, if you're watching the car go around the curve, we don't see an actual force that would be trying to pull someone out of the car. But if you're inside the car, if you're in a non-inertial reference frame, you feel that tug that's pushing you to the outside of that radius. And so what's stopping you, and here's the connection, what's stopping you is, let's say you bump up against the door, and so that door is the constraint force, F sub r, which we said is pointed in the negative E sub r direction. And so that constraint force is what's keeping you on the path as you're going around the curve. If the door weren't there, let's say you're not wearing a seatbelt, if the door weren't there, then what would happen is that you would just maintain your motion and you would fly out of the car. In an inertial reference frame, if we saw someone fly out of the car, then they would just maintain the direction that they're traveling because of Newton's first law. Anything that is in motion is going to remain in motion unless acted upon by a force. And so I want you to get this idea of, in a non-inertial reference frame, you can experience fictitious forces. Okay, this is a pretty common one in which you're being pulled to the outside of the radius. And then as we move on and look at these other terms, such as the 2 r dot theta dot term, we're going to encounter some other really interesting fictitious forces from a non-inertial perspective.